Hey everyone, this is Josh, and today we're going to look at Java's data structures. These are great for knowing how to write efficient and scalable code. We're going to start with arrays. So an array is fixed in size, meaning it cannot be changed after it's created. It's very fast when accessing elements by its index, usually described as O1. It has contiguous memory allocation, meaning that elements are stored in a sequence starting at 0 and up to n minus 1 elements, where n is the total number of elements. It's also best used when you know the number of elements and you know you don't need to change them. And just a quick overview of Big O. When we talk about the efficiency of these data structures, you'll sometimes see the terms like O1 or ON. This is called Big O notation, and is simply a way that programmers measure and talk about an algorithm's speed and scalability. It answers the question of how much slower will this code get as I throw more and more data at it. So it tells us whether an operation is instant, like O1, or whether it slows down in proportion to the size of the data, like ON. So here's how you declare and use an array. So notice that we specify its size up front, accessing an element by its index, like names 1. This is extremely fast because the computer knows exactly where to find it in memory. I also showed a common issue that many programmers run into, which is index out of bounds exception, where we try accessing the index outside of the valid range of the array. So like I said before, the last element in the array will have an index of n minus 1. So like in the example here, we're trying to access index 3 and we get an error because our valid range is only 0 to 2. Going back to our chart here, now what if you don't know the size of your array in advance or you need more flexibility? That's where an array list and linked list come in. Both are part of Java's collection framework and implement the list interface, meaning they maintain insertion order and allow duplicate elements. An array list is dynamic, meaning it can grow and shrink as you add and remove elements. It also gives you fast index access like a regular array, which is O1 as well. This makes it the best choice when you need to look up an element by its position. It's also contiguous as an array, hence why it's fast in accessing elements by index. That's because each element is right next to each other in a single block of memory. However, this contiguous structure is also its weakness. Adding or removing elements in the middle is slow, which is denoted as ON, because all elements must be physically shifted over when adding or removing. You should use an array list when your application requires a resizable list and you plan on mainly doing element retrieval and iteration, but don't use if you need to access elements in the middle. Like if you're accessing elements in the middle frequently, don't use an array list. Uh, then you should use a linked list, which is also dynamic, but it doesn't use a single memory block. Instead, each element stores the data along with pointers to the next and previous elements, hence its non-contiguous memory allocation structure. The pointer structure makes it incredibly fast to insert or delete elements, which is denoted as O1. Um, Especially in the middle of the list because you only change a few pointers and don't have to shift any data. The major trade-off is that element access by index is slow, which is ON. To find the 100th element, the list has to start at the beginning and follow the pointers one by one, which takes time in proportion to its list size. So you should use a linked list when you frequently need to insert or delete items, especially with structures where items are constantly being added and removed from the middle or ends. So here's how you use them. So notice that the syntax is similar because they share the list interface. So you can see here has list string array list equals new array list, and here is also list string linked list. So the choice between array list and linked list depends on whether you'll be doing more random access and iteration, in which case choose an array list. Or if you need to do things with more insertion and deletions, especially access in the middle, then choose linked list. You could also declare the variables on the left side as array list or linked list, but it's um, best practice to use list, as you can see here, as it keeps your code flexible, because if you later decide that an array list is better than a linked list or vice versa, you only need to change the right side. And make sure to include a generic type parameter, like right here, if you're only working with one data type. Omitting it loses type safety, meaning if you accidentally introduce integers when you only wanted strings, it would be hard to find that out, leading to bugs in your code. So here in the demo, you can see that we created our array list. We added an apple and we access it using this its index. It's fast. And here in the linked list, do the same thing. This time we're using dogcat, but this is slower. And while getting the first element is actually very fast, basically an O1, I labeled it as slow random access because if this list had 500 elements, accessing the 500th element would be significantly slower. So that would require the system to go through 500 links. So next we have stacks and queues. So a stack operates on a LIFO principle, last in, first out. The most common analogy used to explain this is to imagine a stack of plates. You always add a new plate to the top, and when you take one, you take it from the top. So the last plate you put on is the first one you take off. And a queue, on the other hand, follows a FIFO. So principle, it's a first in, first out. So the analogy for this is to think of a line, and the first person to get in line is the first person to be served. You add to the back and remove from the front. As you can see, they have different methods to add and remove elements. So push and pop are well-known methods for stack. Queue has add or offer to add and remove or pull to remove. Um, in your code, you'll choose a stack when you need backtracking or reversal, like a web browser's back button. And for queue, you you choose a queue when you need ordered processing or task scheduling, like managing documents or waiting for a printer. Notice that queue is an interface, meaning that it provides the contract, but you must use a concrete class like LinkedList to implement it. And a stack is an older Java class, and it's used like any regular class. Uh, so next, here's some demo code. So in the stack example here, we push plate 1 and then plate 2. So we're adding them, and then we call pop. So the program retrieves plate 2 because it was the last item added, uh, demonstrating LIFO for last in, first out. And the queue here models a line. So we add a person 1 and then person 2. And when we call pull, we get person 1, as is shown here. So this shows FIFO. So where the first person in line is the first one served. And notice that in the Java code that while the stack is simple, we used a LinkedList class to implement the queue interface, as shown here. Um, this is common practice because like LinkedList is efficient for adding to the end and removing from the beginning. Finally, we're going to compare arrays with hash tables. So let's start with indexing. So the main difference is that an array is indexed by integers only and stores a simple list of values, whereas a hash table is indexed by a unique key, which can be any object like a string, and stores key value pairs. And as we mentioned earlier in this presentation, arrays are fixed, but hash tables are dynamic. And if you search for a value in an array, you might have to check every element, which is slow, denoted by ON. And with the hash table, using a key makes lookups nearly instant, denoted by O1. And an important difference in their memory is that arrays have low overhead. Hash tables have higher overhead because they have to store extra information like references and pointers internally to manage their fast access and their dynamic size. An array is a fixed size structure that uses contiguous memory. So this is great for things like game boards and where position is everything. And just like with our image processing lab earlier this semester, that's what arrays are good for. And a hash table, because it's dynamic and is perfect for key value storage, things like a dictionary or storing configuration settings, where you need to look up an item by its identifier key, is useful. So here we're using a hash table to store names as string keys to quickly look up integer phone numbers. Unlike arrays that use numbers for access, a hash table stores data in key value pairs. So here we're using a string. Like here we got lucky cat, and the unique key here is an integer, which is 777, which is a lucky number. And the power of a hash table is in its speed. So it's almost instant to the point where like if you had thousands of entries inside this phone book, it doesn't have to search every single one, right? It calculates the location. So when we try to retrieve a key that doesn't exist, like beta cat right here, um, the get method uh, returns null, which is the standard behavior for a missing key in a Java hash table. And we can easily update an existing entry using the put, the same put method that we used to add. So it doesn't add a new entry, it just overwrites the old value with the new one for that specific key, as you can see here. So we got Grumpy Cat 101 here and then Grumpy Cat 101. So things to remember. So arrays, right, fixed in size, fast index access. ArrayLists, they're dynamic, right, and they're good for random access and iteration. Linked list, they're node based, good for middle insertions and deletions. Stacks, they're last in, first out, so push pop. Queues are, think of the line, right, first in, first out. And hash tables are key value pairs. They're fast lookup using hash functions. And that's all I have for now. Thank you for watching.